Welcome to the webinar. You have entered as an organizer and may now speak to any other organizers or panelists on the line. When you are ready to begin the presentation, press the Start Broadcast button on the GoToWebinar control panel to allow all attendees to hear you. This system will notify you once you begin your broadcast. The broadcast is now starting.
So this webinar will be covering concepts related to checking or accounting for mass balance within a flow system, or a system that has flows of usually water, but could be other things, a network of points in which we have material or water flowing between them, and through storage elements within the network. So the purpose of this webinar is to help you understand the importance of checking for mass balance in a gold sim model, and then also how to do it, best practices for doing it. We will be drawing from two existing models from our library. So let me just review what those are. If you go to our webpage, Customer Care, Learning Resources, and then Model Library, the sub-tab down here, scroll down until you see this link for applications, and then it takes you into the model library. And the two models that I'll be talking about are in the section called Water Management. And the first one, it's moved to the top. It's called Check for Mass Balance. That's the component that you can use to copy and paste into your model, and then connect the inflows and outflows and change in volume to ensure that you have mass balance. And then it does some extra things for reporting, which I'll talk about in a bit. The other one that I'll be showing you is just an example model, and also in the same category. If you scroll all the way down, it's called Network of Interconnected Ponds. So this, if you wanted to use the examples or look at them after this webinar, you can download these two models to learn more about them. This model has a dashboard, but I will go ahead and describe that later. Okay, so for now, what I want to do is first I want to talk about I think it might be best if I talk about the system that we are modeling, and then talk about how to check for mass balance. So in our case, the system that we're trying to model, and I'll zoom into it here, is a network of flows, which is shown here with these containers. We have a stream, which is on the left here, flowing from the top down. So you see there's an upstream, there's a diversion, and then there's a downstream point. Water is diverted from the stream into a pond. Overflows from this pond, if it ever gets too full, will flow over to pond 3. And this sometimes happens because we don't necessarily control the flow that comes into here, because there's other flows coming in. So we can easily control the water flowing from the diversion, or the flow rate can be adjusted from the diversion. We can reduce the flows as the water level in the pond approaches the maximum capacity, but we also have other flows coming in, and so it can overflow, and when it does, then it's simply just overflowing over to this other pond. You could also look at these two ponds, 1 and 3, as a single storage element. If you combine them, they do have some linkages here that causes some restriction, but you could also look at them as a single one. We also have water pumping back to pond 3 if pond 1 is low. So there's some logic here that pond 1 communicates, or not logic, there's a state that pond 1 communicates to pond 3 to say, hey, I need some water, bring it over. So it does. And in this process, we have what's called a feedback loop, which we'll want to talk about a little bit for this model. It does, or could, impact how we account for a mass balance, amazingly enough, which we should talk about. Next one is another pond down here that supplies water to demand A and demand B. So this pond is telling the pond 1 that I'm low on water, I need more. So there's communication coming from pond 2 over to pond 1 to say, I'm low, I need more. So water gets sent there. Then this pond is continuously trying to feed the demands for A and B. A consumes all the water, so there's nowhere for that water to go once it hits this demand. It's all consumed. On B, there's return flow. All of it is returned, but only some of it makes it back into the system again for recycle. Okay, so that's the whole system. But all of these points, there's more going on, obviously, because they're in containers and there are more calculations inside of these. But it's important to note how this model is built, showing you only water flows. I told you multiple times that there were some states being, there was some information being passed back to other places, and we do not show the influence lines of that information because I have moved the reference to those the states of those components up to the parent container. So if you look at the hierarchy of this model, you see that we are inside of this container called system model. That's what we're looking at here. But adjacent to it is a container called information references. So anywhere that we are passing information to say, hey, I'm low on water, I need more, or whatever that might be that's not related to a flow of water, I'm passing that reference up into information references. And then it comes back down to the place where it needs to be communicated to. So just imagine it going up like it's like sending a radio signal up and then back over instead of an actual influence line that GoldSim draws. So that way, I've isolated only the flow influence lines in this model to describe to the end user that looks at this model that, hey, this is what's going on with the water flows in this system. If we want to see what kind of information is being communicated back and forth, then we would want to go up one level. So there's various ways, as you know, to go up one level, right? I can click on the parent container here, or I can click on the up, or I can click on one of these items here inside of this container. These are all sibling containers because they're side by side here. Okay, so we have the system model where we were just in and the information references. So we were passing information out of the system model, things such as the water level in a pond. If I open up the influence line, you can see here that this is an information regarding a request to pump water. In this case, it's a request to pump water into over to pond 2. So that's where I was telling you that that pond 2 is supplying water to A and B, and when it becomes low, it needs to tell pond 1, hey, I need water, so bring water down. So that is one piece of information, essentially saying that I'm low on water is what it's doing. We have another one that is telling the diversion structure that, hey, demand A is highest priority. So that information is getting passed over to the diversion. And then there's another one that's pond 1 telling pond 3, I'm low too, so I need water coming back from pond 3. So these are just, consider them state variables. This is the state of various components of the model that is really just information that needs to get passed to another place in order to control what kind of flow is coming out of it. and going to another place. So we pass that information over to our information references, which if I open it, you'll see it's just a place to house these references. That's all it is just a reference, but it's a reference that's outside and away from the system model so that this feedback can happen at a parent level and not conflict or confuse the end user and make it more difficult to understand how the system works when it comes to where the water is flowing to. So that's what we're trying to convey to the end user is where does the water go? How is it flowing around? So I wanted to spend a little bit of time there. I know I've talked about this in other presentations before, but I just want to make sure that everybody understands that's how this model is set up. The other reason I wanted to talk about that is because setting a model up like this makes it a lot easier to account for a mass balance because we have all the flows accounted for in this one place, and it's not being encumbered with influence lines from information to make it more complicated and more difficult to see where the water's going. Now, there is one difficulty here, and that is we have some water that is coming from outside of this system and also that's leaving away from this system. The two things are actually three. There's flows that are driving the upstream flow, the source essentially of this water that's coming in. So there's a source coming in here, and what I'm going to do is use an arrow to identify an inflow that comes from outside. I need to move. I'm going to use an arrow that indicates flow that's coming from outside. So I'll just change this to a green color, and then I'll use a dashed line and then give it an arrow symbol. Okay, so this kind of symbol, and I'm going to make it a little bit smaller. Okay, so this kind of symbol, I'm just going to put it next to that container to indicate that water's coming from outside. Another thing I could have done is, colored this with a fill color by changing the appearance of the container. There's multiple things you can do, but I'm just going to put that there. And then there are places in this model where we have water that is leaving the system. So I'm just going to change this symbol to be the opposite, sort of opposite, red. And then we can put these next to the containers where we have some water that's leaving the system. In this case, all three of the ponds have some evaporation that is leaving the system. So somebody is asking, does anybody have a question? I see a hand raised. If you have a question, please feel free to type it in to you should have a way to chat in here. Feel free to type in any questions that you might have. But I was just going to copy these to the various locations where we have flows leaving. And this is really just to indicate on our system where water is leaving the system. And in doing this, and it might be ridiculous to do it if every single element has some evaporation, right? If every single container had evaporation going on, then it would just be, well, what's the use of marking every single one? We would just know that they all have evaporation. But in this particular model, we have evaporation from these ponds, we have water demand where the water is consumed, and then we have the downstream flow where water leaves the system. But in marking the system like this, now we know where at the boundary of the system where water comes into it and where water leaves it. And this is important for the doing the mass balance check. Okay, I don't think we have any questions yet. Okay, all right. So now that I've marked it this way, now we are ready to do an accounting of mass balance. So in addition to knowing where the inflows and the outflows are from the system, we also wanted to know where the storage elements are. There are two types of storage elements in this model. One is a pool or reservoir, and those are in each of these pond containers. If I go into the container, you see there's a pond, or actually a pool element. So we need to account for the storage, the change in storage in each of these ponds. And there is one more place, and that is where you have a delay. Any material delay elements like this contain some storage over time, and that is the amount in transit that is part of a material delay. Material delay is always carrying some, if there's flow coming in, the delayed the delayed amount is the amount that's in transit before it comes out the other end, the amount that's being delayed. Yeah, so we'd want to account for storage at that point as well. Okay, so yeah, so the essentially what we're doing here is we're saying, okay, we have a system that's contained, and we could even draw a box around this, right? We could draw a box around this and say, well, this box automatically got put on the up to the front, so I'm just going to change this to be in the back. There we go, and give it a dashed line. Okay, so now that we have this defined, I'm gonna make that a little thicker. Okay, this is our system, right? And what we're trying to do is say what flows are crossing that line, essentially. And in our case, we have evaporation, which goes into the atmosphere. That's crossing the line. We have flows coming into the stream, that's coming through into the system across that line, and then the downstream flow crossing that line. Yeah, so that's what these little lines are indicating. Okay, so now that we have those accounted for, we also have looked at where our storage elements, both pool elements and material delays, those are the places that we have storage, water being stored for some amount of time. Okay, now that we know all of those things, now we can do a mass balance accounting. All right, so I'm going to the very top level of the model, and I'm outside of the system model now. I'm at the root level. This is the very top level of the model. I want to come out here because there's no reason to further complicate or make more complicated looking the flow system itself by incorporating a mass balance check inside of there. At least I don't think so. I would prefer to keep it as clean as possible, especially if you have to iterate to solve for the flows in the system, and you just want to keep it as lean as possible. That's my opinion, but you don't have to. You could do the mass balance integrated within the system and account for things, but all it's going to do is just add more influences, and it will make it more complicated. So I would prefer to keep it outside, and you'll see there's a container out here called mass balance check. And this is essentially where we're just referring to flows and storages in our system to just do an accounting, just to check it. That's all we're doing. And that model was just copied into this container from our library. So let me just talk briefly about the mass balance check. So now I'm going to a totally different model, and this is what you find in our library if you want to copy and paste the mass balance check and use it in your model. This model has, at the very top, it has a very simple system to just make sure that the calculations are working properly, but you can ignore all of it. All it's doing is saying, well, let's just try this thing out and make sure it works. It's just a test. But all you need to do if you're going to incorporate this in your model is just go into this container and do a Control A, right, to select everything, and then Control C, and then paste it into a container in your model. That's all you need to do. Then you'll have some broken links. These things, this inflow one will be broken, and your links in here will be broken. In fact, perhaps the best thing to do here would be, I should have done that already, is highlight these elements. So these are the elements that you need to modify when you paste this into your model. You don't need to touch anything else. You shouldn't have to anyway. Okay, so for the inflows, then in our model, we've already delineated them. All we have to do is just go reference them, put them in here. Outflows, same thing, list them all here. And then the change in volume is the one that's a bit more tricky because we need two pieces of information for change in volume. You're going to need the initial, the starting volume at the beginning of the simulation, whatever that number is, and subtract that from the current volume. So that's what's happening here. The other way around, sorry. It's the currently calculated volume minus the initial volume, which is it's going to be a static number. Initial volume is going to be static. If it's 0, you could ignore this, but I would say don't, because in the future you might change the initial volume. So it would be vital to have it here in case you do make it a non-zero value or positive value. Otherwise, if you ignore this, because it's 0 right now and you ignore it, and then later you go and you make it a value greater than 0, well, now your mass balance will report an error here. So it's important that you have that. In fact, maybe what I'll consider is modifying this model a little in our library so that there's a place to put initial volume separate from current volume, and then this will calculate change. That's probably a good idea. I might do that. But anyway, it's really important that you remember to do that. For each one of your reservoirs, you'll have a separate equation like this, or you can just list all of add up all of your current storage element values. And I call it reservoir loosely here. It could be named whatever. It's whatever storage elements you have. They could be pools, they could be integrators, they could be reservoirs, and they could be material, delay, mass, and transits. All of those things need to be added here, and then subtract from all of those their respective initial amounts, initial quantities. So that equation must be done there. Once that is all done, then we just do the mass balance equation, which is inflow minus outflow minus change in volume should be 0. And in the case of GoldSim, it should be close to 0. What we should be seeing here, and if I run this model, let's see what we see. If I right-click on mass balance and show a time history, then yes, what you see is a very small number, very close to 0. There's some numerical error, but we're essentially 0. It's 1 times 10 to the negative 14. So that's a lot of zeros in front of or behind the decimal point. So this mass balance checks out. And by the way, it checks out because what we do is we check to make sure that that mass balance number is less than or equal to an allowable error that's defined here. So this can be adjusted by you as well. What we're saying in this particular model is that our allowable error on any given time step is 1 liter. As long as we are below 1 liter on our error with all of the elements we're looking at, then we have a mass balance. So we use a milestone element here to check to make sure that we achieve that condition of being less than the allowable error. So the way that the milestone works is it says, okay, we're going to trigger when you tell us to trigger using a trigger definition. And in our case, it is going to, on every single time point, it's going to check to see if we have a mass balance value greater than the allowable error. Just to make sure in case we have any inserted time steps or whatever might happen at any point in time, it's going to be checking that every single time step. And there are other ways of triggering this. We don't have to do it that way. But in this case, it will, even if you have an inserted time step, unscheduled event occurring, it's going to be looking for that to try to find it. Then when it happens on the first time and only on the first time that happens, it will report to you the time, either the elapsed time or the date of when that occurred. So you can look at the outputs here and it shows you E time date. That's when it first occurs. So it might be important to know when that occurs. We use a script element now to report to you an error. Okay, so let's just have a look at what an error might look like. One way to do that is to go up a level and just do a check. Now, this mass balance check is intended to look for both discrete changes and flows, because you could have a discrete change that you need to account for as well. Typically, that's not the case with a flow network model, but sometimes you do have them. So that's one of the reasons why integrators are used to do the accounting, because integrators have the ability to accept discrete changes. So on the outflow side, we have a discrete withdrawal request that's being made on the system that we also want to account for. The other reason to use integrators is because they will capture flows at every time point and calculate their cumulative amount over time. Even during an unscheduled event that might occur, they will capture those flows. So it's really important to use them in this particular case, because if you did not, and if you're only subtracting the instantaneous flows, if something happens between a time step, it may not, you may miss it, you may not report it because you might only be checking things on the time step. Now, I have multiple checks in here to make sure that doesn't occur, such as what I was telling you about the milestone. It's looking at every single time point, even unscheduled times. It'll try to find when you have an error. So that's kind of a way to get around that, to check that. But mostly you want to use these integrators on checking the flows, because it will accumulate everything, even flows that are occurring during unscheduled steps. Somebody asked, if we have discrete changes in the model, do we need to update that in the integrator element? So add those two integrators to the list of elements to, yeah, if you have discrete change flows that are leaving the system or coming into the system, yes, they need to go into, you need to add them. If you have a discrete change flow leaving the system, I'm not talking about moving from one element to the other inside the system. That's not going to be a problem for us. It's only if you have a discrete amount leaving the system or coming into the system at the boundary. Those do need to be added to the integrator here. Yes. Yes. So, okay. All right, so moving on. Now that you understand how this is calculated, I wanted to show you the script element. We have this data element called exception handle type, and what it does is it just gives you an option to, how do you want to report a mass balance error? Would you prefer that it adds it to the run log without interrupting anything else? That's kind of the softest way to do it, and that's a number 3. So if you give this a number 3, then that's what it's set up to do right now. It'll just write it to the run log. So I'm just going to do that now. Let's see. If I add a value here, yeah, that's what it was. So if I add 3 cubic meters to this, then we're going to add, and this is an error, essentially. At 0, we don't report any errors, but I'm pretty sure this should throw it. Let me just see. Yeah, okay. So I ran this model. I gave it this is just a test to make sure that we throw an error, because this discrete change that I have right here is not accounted for in our mass balance check. So adding any non-zero here will throw an error, just to be able to test how it works. So it's telling us right now, after we run the model, that hey, everything ran fine, except you have something in your run log. Do you want to see that? We say yes. So now we look at the run log. Okay, so now we look at the run log, and it has all the normal stuff here at the top. But then if you scroll down here, warnings and errors, you see it says mass balance check, MB error message, script warning. Okay, so this is coming from that script element. It says mass balance error of 3 cubic meters, negative 3 cubic meters at 31 days. of the simulation. So it's telling us some good information here. It tells us that we're off by -3 cubic meters, and it happened on day 31. So that information can help us debug the model and find where that problem is. And so another thing you could do is plot a time history of the mass balance to see it. And so you can visualize, okay, there's something not accounted for here at this point. And so it's happening on day 31. And so then you can go into the model and try to figure out, where did this happen? We can see right here on day 31, there's this jump in the storage. So something is being added there and it's not accounted for. And it's this thing right here, test error check. So anyway, we don't need to get into that too much, but just know that's how the message is being reported as an error report or a warning being written to the run log. Okay, the next type is a number 2. And there's a note in there. Number 2 is a warning with a message. Let's see what that looks like. So we run the model, and then we get this, a little pop-up that says mass balance error of 3 cubic meters at day 31. Same message, but it pops up and interrupts the model. You see we're in run mode right here. The model is not completed yet. Then I click OK, and you see it completed the run after the interrupt was clicked through. And then it also adds a message to the run log, same message. Okay, so if you want it to interrupt, that's kind of more in your face, right? Makes it more important. And then 1 is the most urgent type of exception that we're going to handle, and that is a fatal error. And so if you want it to produce a fatal error, that would be the safest, right? To make sure that, okay, we're not even going to run this model if you have this issue, right? We want to deal with it now. And so what it will do here is it will say, okay, here's the message, but then it's also going to point to you in the script element where that came from, which is not as useful in our particular case, but it would be good just for you to understand how that script is working. So here's the script element. If you've never used a script element before, just know it's kind of like writing a text file script, but it's a much more controlled environment. We control what the syntax is. And you just have to fill in the blanks, essentially. We make it a lot easier for you to write scripts and not make a syntax error. So if you want to add an if statement, for example, you just come down here to insert and put if statement and so forth. But all we're doing here is we're just saying, hey, look, if we have a mass balance error, if our milestone is triggered, then enter into this if statement. Otherwise, don't even worry about it. We're not even going to go into this. But it did happen. So we went into here, and then it says, okay, let me move it over here. What type of exception are you going to do, a 1, 2, or a 3? So depending on that number, it goes into one of these sections. And then in a script element, you can choose how to report a message, either logging it in the run log, showing it with a message, or interrupting the model as a fatal error. So those are the 3 that we have in here. And then the nice thing about these messages from a script, better than an interrupt element. Okay, interrupt element could also be used here, by the way. But the nice thing about a script is you can provide an output that is context aware and provide values that are reported from outputs in your model into the text of the message, which is nice. So you do that with a curly braces equal sign. Anywhere that you put a curly braces with an equal sign, then in between the curly braces, you put the name of the output in your model, and then it will report, it'll write that value in. By the way, it doesn't, if it's a unit-based value, it will report it always in SI units. Just keep that in mind. So if there's a case where you don't want it to report SI units, then you should do a conversion outside of this script, or no, outside of this line, maybe just inside the script even, and then cast the units off so that it's a unitless value. Then it won't try to convert it to SI, just so you know that. But very handy tool, very nice way to help you point to where the error is. It's very helpful in these cases to do everything you can to point to point to the problem. Okay, so that's how this whole mass balance model works, which you can copy from our library and put in your model. But now let's go back to the original example I was showing you, in which we're doing this real mass balance check, the real thing. And I'm going to introduce an error that is subtle and difficult, could be difficult to understand. And in fact, maybe I'll walk through a couple of them. The first one I want to walk through that is common is just a simple just user error of just forgetting to include one of the outflows that's occurring in the system. Before we do that, let's run the model and just make sure that it works properly. So I'll do that. I'll run the model, and you can see it went all the way to simulation complete with nothing telling us there's any messages in the run log, right? So because of that, I already know we don't have any mass balance issues. So I'll click OK, and I'll go into the mass balance check, and then I'll plot the mass balance, and it shows very small numbers. So we're okay right now. Okay, so everything is good here. And let's see, my allowable error, by the way, 1 liter. Yeah, okay. So right now we have no issues. Let's go into the mass balance check and just take a look at the inflows and outflows. So if I go to the inflows, you'll see that I have only one that comes into the system, and that's that upstream flow I was telling you about that comes into the river, that's driving the river flows. So that's the only inflow to this entire system. Oh, I see. I have some graphical issues here. There we go. Maybe a little more. Okay. All right. So by the way, if you get tired of moving graphic objects in GoldSim, you can always right-click on the graphical object and go to Appearance and then Locking and lock the appearance. And once you do that, you'll see my cursor does not change when I click on it. You can still select it and do things like copy to the clipboard and stuff, but you can't move it. So if you would no longer accidentally move the thing around. There, like that. Okay, so we have the one inflow, and then we go to the outflows, and you see that we have how many? 5 here. And so we've got the evaporation rates of the 3 ponds. We have the consumed water from one of the demands, and then we have the downstream flow of the downstream end of the system. Well, let's just say, for example, that we just forget one. We just forgot about pond 3 evaporation. I'm just going to delete it. Okay, so there's nothing in the model that says, oh, hey, I have an evaporation that's going to nothing. It's not being referenced. But we should just consider that for a second. Let's go over, I think it was pond 3 that I removed the evaporation from. So if we look at the evaporation rate, this evaporation rate, what is it affecting? It's only affecting pond 3. Okay, that's because we have in order to calculate evaporation, you have a feedback loop inherently in the model because evaporation is a function of the volume in the pond, right? So that's why we have a feedback here. But if I click on the output ports here and go to the outflows and look at the evaporation, you'll see that there's no like a little dot next to this symbol indicating that this flow rate is not going anywhere. It's not talking to anything. And compare that, by the way, to a different pond. Let's look at one of the other ponds. And by the way, you can do that. I don't know if you saw this. This is kind of a new feature. If you click on these arrows in the address bar up here, you see that you can pick other containers to go into. So let's say I want to go right into pond 1. I click that. Now I'm in pond 1. And if I go to the outflows, look at the evaporation, you see there is a dot here indicating that it is affecting something, in our case, the mass balance. Okay, so we've traced back the evaporation from pond 1 over to here, but we saw, however, that the pond 3 evaporation is not being accounted for right now. So when I run this model, what will happen? We will get a warning, and we have the warning that says we're not going to interrupt the model. We're just going to tell you there's a warning message in the run log. So when we display it and scroll down, then you see the script warning is telling us mass balance error of this much at this time. Now, this message is not as this is using an older version of the mass balance a tool that I was just showing you. So I'd probably want to replace this with a newer version that tells us the day in which it occurs instead of number of seconds. So that's less than useful to show us how many seconds into the simulation. So I would probably change it to what the latest version of the mass balance check does, which is showing us how many days into the simulation that we have a problem. But anyway, when we look at the mass balance and plot it, you'll see that there's a continuous error occurring here in our mass balance, quite a bit of error. Now, this is a very small system, so 7 cubic meters is a big deal in this particular model, but you can see it's occurring constantly, pretty much, except for maybe a short amount of time over here in the middle, but it's pretty much constantly causing an error, and it's constantly a misbalance. So in this particular case, we would look at this and we'd say, well, we're looking for something that is continuous. It's not discrete. It has nothing to do, it's probably not an overflow, because overflows are often occurring in a case where you hit a bound, an upper bound. And so if it was an overflow, you'd see jumps. If it has anything to do with perhaps like a pump station, you would see it stopping and starting, you know. So this gives us clues already to what it might be. It's going to be something that is a continuous function. And the only place in my model that I have continuous functions like this are going to be evaporation rates currently. So that would be something to look at. And so anyway, I can go ahead and add that back in to our outflows. And this was, whoops, pond 3 evaporation. And I'm just going to connect directly to the pool element's outflow of evaporation. Pond 3 evaporation. Okay, run the model just to check it, make sure it works, and it does. Okay. Somebody asked, can this mass balance check be used with species in the contaminant transport module? Is there an example? Okay, well, when we're talking about the contaminant transport, what I would say there is the CT module inherently should be correctly accounting for mass fluxes within GoldSim itself. You shouldn't, that should be automatic. It is automatic, actually. It does that. That's part of the module, what it does for you. So you shouldn't have to do that. I mean, you could do it on the side if you want. And the answer to your question is yes, you can do it. Although these we're working with scalars here. We're working with one item, and usually a species, well, actually always a species in a species list in GoldSim CT module. That's always a list. It's an array. We call it a vector. You'd have a vector of items, right? So if you wanted to account for all of them, then you'd have to convert this model into a vectorized mass balance. You can do it, but what I'm trying to say here is you probably don't need to, because the CT module takes care of that for you. It ensures that that you have a mass balance in that case. So, but to answer your question, yes, you could do this with any type of flow of any material or parts or rocks, or it doesn't have to be water. You know, it could be anything. It's just the same. It would be the same concept, but not something you should need to do for CT module for tracking the species contaminant amounts. And I'm talking about the mass fluxes between cell pathways in that module. You wouldn't have to. Okay, so all right, so now we don't have an error, but in this particular model, we're doing something a little bit tricky, and I don't want to spend a lot of time on it. We are getting close to out of time, but I just wanted to make a note of it. There is one place I mentioned earlier where we have a feedback loop, and that is between pond 1 and 3. We have overflow that's instantaneous going over to pond 3, and then we pump water back. That causes a recursive loop, which requires that we break the loop either with a delay or with a previous value. And now a previous value element is going to cause problems for you. It could. Now I have one here. Here's my previous value element. This is what I'm using to break the loop. This is my pumped water going back to pond 1. And I am using a previous value element to get that back over to pond 1 without causing a recursive loop. But as you might know, the previous value element is a delay of 1 time step. Inherently, that's what it is, because it's grabbing the value that was last updated, which happened on the last time step. Unless you're in my situation here, which is that I'm looping the container. But let's not worry about that at the moment. Let's just first talk about the fact that we have a previous value element and what this could do to our mass balance check. This is important to note because essentially what's happening here is that we are referencing a previous flow instead of the current flow. So what happens between those two times could amount in a slight loss or gain. And let me show you what that could look like. So I'm going to go up all the way to here. We're inside this thing called looping container. And I am just going to, for now, let me move these. I'm going to just change a couple of things here. Don't worry too much about right now what I'm doing. I'm just going to completely wipe out this functionality of looping from this container. Let me just make sure it still runs, and it does. Okay, so I run the model, and now we have this message. I look at it, it says there was a mass balance error of 2 cubic meters pretty early on in the simulation. If I go to the mass balance plot and look at it, you'll see I have these strange misbalance flows occurring here. And because it's not systematically moving up or down, it pretty much ends at 0. Well, it's up at 2, but if I went a little bit further in time, it would probably go back to 0 again. So it's not causing a systematic error that is growing or decreasing over time. It's always coming back, so it's not causing major issues, but it's still not a mass balance, right? And the only reason for this is because of the delay we have at that previous value element. Now, if I used a material delay, then I can account for any delays using my total storage accounting here in the initial volume. I would put the mass in transit. In fact, we have one here. If I look at total storage, you see that there's a mass amount in transit output that's being used here. That's accounting for the delay from the return flow from demand B. But anyway, this previous value element, we don't have an easy way to account for that. I mean, we could put that in here, but what I'm trying to show here is that previous value elements should be avoided if all you want to do is just delay a flow in order to break a recursive loop. You should use material delay elements and then account for them the way I have done here. And that is the correct way. However, it's possible that you can use a looping container so that the previous value element will just read the value from the previous loop at the same point in time. That way, you have removed the delay completely in that particular recursive loop situation. So this is useful when you have a large time step in your model and you cannot afford to have a delay at that point. So it's kind of a workaround, but it does work in many cases. And what I'm going to do here is I'm going to watch the difference between the previous value element and the current value that it's reading. And I'm going to loop the container. I'm going to repeat all of the calculations over and over until the previous value element output equals the current. Okay, So to do that, I have this element called convergence that's going to be looking at the difference between the output and the, these are, well, I need to just go do a function of, I go function of, then you'll see there's this element called discharge to pond 1. And that is the amount that we're trying to discharge from this pond 3 over to pond 1. And we're going to reference it with a previous value element. So I just want to compare, and maybe if I move that in here, yeah, we're gonna get some errors. It's okay. Okay, I want to compare these two. This is the current value. This is the previous value. If I loop or iterate this container that this is in, then eventually these two will be the same value on each time step after so many iterations. Okay, so to do that, then I will go, well, first of all, I have some errors because I moved the element. So pond, yeah, I need to reference that now. Pond 3, because I moved it. Okay, everybody's happy now. Okay, all right. So then what I'll do is I'll loop this container, and I will loop it until the previous value element value equals the current value. So I'll just refer to that convergence expression there. And it's also a good idea in case there's some error in the convergence or whatever to say, or loop count is greater than 100, just to make sure we don't loop on forever and ever and never stop. So with that, and I want to report how many loops we've done. So I'm just going to put that there so I can report it. And now we run the model. Now you can see we have no error, because if I look at our convergence, you can see that we are always the same. And then also, if we look at the loop count, you can see that there are times during the simulation when we have a different value at the previous value element versus the current value. And so we repeat all of the calculations to get the same value. And there was a couple of points where it required more than a loop, more than one iteration, more than one repeated iteration. By doing it this way, we don't loop during some times of the model. It's not necessary, so we don't loop, but in other times we do, just when we need to. So this would be a pretty fast way to accomplish that convergence. Okay, so with that being done, now we do not have a delay. We don't have a delay between the flow that's being referenced using the previous value element and the element itself. And then we also have a mass balance in this model. So, and I can plot that, and you can see we have mass balance. So that's good. One last thing I want to say is in a real model that is more complicated than this one, it's a good idea to break your model into smaller segments. And I don't mean physically, but I just mean do a mass balance of segments of the model separately. The reason for that is because it will point you to the general region of the model that might be having a mass balance error, which can be very helpful. So in this particular model, I'd probably break it into 3. Maybe up here, pond 1 and diversion and upstream, that would be 1. You want to break it into sections where you don't have too many flow lines. So one that might make sense is maybe around these 3 ponds. Do a mass balance around these 3 ponds by itself. That means you need to account for the flow crossing this everywhere you have an influence line crossing this boundary, right? You'd have to account for the flow here. These are outflows. Here's an inflow. Here's an inflow. And then of course any of your move this back. Any of your flows leaving the system, those would also have to be added. So you can do a mass balance of just this part. And so then when you get a reporting of a mass balance error, it would tell you which section you're having an error in. So that would be a good way to do an accounting, and it should also be done while you're building the model. That is the easiest way, I believe. And then as you add flow components, then you can add those flow components to your mass balance, but do it in the stepwise fashion so that every time you run the model as you're building it, you're ensuring that you have mass balance all the way from the beginning. It's a little bit more difficult to incorporate a mass balance check after the model is already completed. That's what I have found in my experience. So that concludes the presentation. I hope that was useful. I do appreciate any feedback or comments or questions that you might have, so I'll wait around here a bit to field any of those. And then you can also follow up later, but we will be posting the recording of this video or of this presentation after probably posting it either tomorrow or Monday. Thanks for joining us, and we hope to see you next month. Somebody asked, is it better to do the mass balance on a group of ponds or individually or both? Yeah, this was asked in the previous session. Somebody was asking, well, why not just do a mass balance on each container? And that could be useful if whatever's going on in the container is very complicated, but if all you have in there is one storage element, I think it might not be very useful. I mean, it would be good to it's always good to have more, but I think that's just going to be extra work. So I would say a group of ponds. Yeah, I would say do it around a group of ponds because you're probably not going to find issues within just a container. It's unless it's really complicated. Um, it's too small of a point. Usually where you have problems is where flows are passing from one node to another. So you want to incorporate in your smaller mass balance checks, you want to incorporate multiple containers, I would say, or multiple, objects within your flow system, if you can. If you can do it that way, yeah, that's how I would do it. Somebody asked, would the process for checking vector inputs, for example, chemical parameters, be similar, or does this only apply when scalar? The current example that we have right now is for scalar outputs, but converting it to a vector would be fine. I don't see any, let me go to it. Okay, so mass balance check. Okay, so to convert all of this to a vectorized mass balance, I don't see any issue at all. I think all of these elements can support a vector except for the when we get down in here, but we could deal with that in a different way. All of the rest of these things could very easily, well, I don't even know why I have that previous value there. Okay, all of these other things can be converted to a vector or a matrix even. So you could definitely do all of this as a vector. So the mass balance would be a vector output of all of your chemicals, for example. And then you could come down here and instead of saying, instead of triggering on when you have a mass balance issue, you could do a sum v, sum of the vector items, make sure that's not greater than the allowable error, something like that could be done. So you would have to roll up all of the numbers here into a scalar at this point. There are other ways of doing it where you could do a reporting on every single item of the vector, but it would have to be built a different way here. But you could certainly do it. And it wouldn't take very much work to convert this to vectorized. That's a good question. Thanks. All right, any other questions?